Thank to the organizers for the invitation to deliver this lecture. And as the title says, we have some new examples of rigid varieties and some interesting questions. So let me explain first what is known about rigid varieties, especially rigid surfaces. So I will be instructional in the first part. So X is a compact complex manifold. And there is a deformation, the definition of deformation. Of X is the following. Deton is a proper smooth family, proper smooth holomorphic map, where B is a connected analytic space, which could also be non-reduced. And if we denote by xt the fiber over the point T, we also give an isomorphism of X with the fiber over a certain point T0. And so rigid means that it doesn't have deformations, but one has to be a little bit cautious. So first of all, a deformation is said to be trivial this means that there exists, so in the deformation there's B, then there is a fixed point, so one should really think that this is a germ of an analytic space, and trivial means that there exists an open set B prime containing T0 such that the family is trivial over B prime. So if you take the fiber product or the inverse image of B prime is isomorphic to X times B prime compatibly with the projection onto B prime. So we come to 4 definitions of rigidity. So this is another definition. We have X is rigid if every deformation is trivial, of X is trivial, and 2, X is infinitesimally rigid if the first cohomology of theta x is 0, and theta x is the sheaf of holomorphic vector fields. Now, before I continue with 3 and 4, I should give another definition, which is due to Kodaira-Spencer. So, X deformation equivalence is the equivalence relation generated by the following: X is deformation equivalent to X prime. This means that there exists a deformation of X and T prime in B such that X prime is isomorphic to X over T prime. So we get this parameter space over T0 that is X, and there is another point T prime, and X prime is isomorphic to this fiber. So we say, Kodaira-Spencer says that they are directly deformation equivalent, and then there might be some chains. Well, with connected, it's already an equivalence relation. So, the third condition is global rigidity. This means that if X prime is deformation equivalent to X, then X prime is isomorphic to X. And the fourth notion, I will give a slightly weaker, because I don't want to enter into too much details. I say that X is strongly rigid This means that if X prime is homotopically equivalent to X, then X prime is globally rigid and belongs to a finite number of isomorphous classes. So a typical example would be compact Ball quotient, and then this is a theorem of Siu, Mostone, that in this lower dimension, it's really, if X prime is homotopically equivalent to X, then it's either X or complex conjugation. Now, in higher dimension, the number of complex conjugations blows up, and this is why I give this definition.
Do you know an example of something which is strongly rigid and which is not locally symmetric?
Of something which is
Strongly rigid and not locally symmetric?
The master suit.
P2, the projective space, they're compact duals, yeah.
Okay,
So, something which is globally rigid, you said? Sure. I will come to this. It's these examples this relates to the previous talks. There was these examples by Mosto and Siu, which were very close to the ball, and they have negative curvature, so the universal cover. In fact, this motivated a lot of search for this. This is related to Rouleau's talk. People thought that if you are close to this Bogomolov-Miyaoka line, then the universal covering should be R4, okay? Okay, so it's rather obvious. So, well, 4 implies 3 just because I put it in the definition, and also now I realize when I explain things that globally rigid implies rigid by a theorem of, I think, Grauert and Kerner. And then, moreover, infinitesimally rigid implies rigid. And so the 2 implies 1. This was proven by Kodaira and Spencer, but more generally follows from Kuranishi theorem. That all deformations are induced by the semi-universal deformation with base. So since this is unique, with base called the Kuranishi space of X, and this is a closed analytic set, so this deformation of X is the 0 set of a certain holomorphic map. Psi is also called the obstruction map, goes from the first cohomology groups of the sheaf of holomorphic vector fields to H2 of Gx. So in other words, we get in this complex vector space an analytic set defined by as many holomorphic equations as is the dimension of this. So H1 of Tx is the Zariski tangent space. To the deformations of X. And so if 0, then the deformation of X is just a point. And all deformations are trivial. Now, the reason why I mentioned this more general result is due to the fact that it gives an inequality conjectured by Enriquez and fully proved by Kuranishi, and we have this Enriquez inequality Enriquez-Kuranishi inequality, where in Cn we have m holomorphic equations, and these vanish at one point, then the dimension of the deformation space of X is at least n minus m. No, sorry. N is this, so it's H1 of theta X minus H2 of theta X. I will return to this inequality in the case of surfaces. So it might happen that somehow the deformations are just a discrete set, but there is no rigidity. So also for the first theorem which I want to explain, it is important to consider the class of rational ruled manifolds. Considered by Hirzebruch, Vaccaro, Seger. So the basic example is Fn, which is the projective bundle associated to the vector bundle on P1, OP1 plus OP1n. In this case, the deformation space of Fn is a germ of a complex manifold and this vector space is x1 of OX and OP1 and OP1. Now, this is the same as H1 of OP1 minus n, which is dual to the space of polynomial of degree n so this is C to the n minus 1, for n is at least 1, and for n equals 0, we get 0. So the polynomials of degree n minus 2, and so either it's negative or you have to add 1 for the dimension. And in this is my favorite example, because what do these extension classes here parameterize? I take xi, and xi parameterize a vector bundle of the form OPN v xi OP1n. And so to xi, you associated the vector bundle of rank 2. It's a direct sum, but in some other way. And so to xi, you associate P of V xi. And it turns out that this is just some Fn minus 2k. This is easy exercise to see. So you see F2 can deform to F0, and we want that this is non-negative. So F2 deforms to F0, F4 deforms to F2 on a cone, and then the general is F0. So there is a, so this shows that there is something to take care of, is that if you look at germs, the deformation equivalence is not symmetric, but as I gave it, it is a symmetric. So you see that if you take F2, which you can think as a cone with a singularity, a small deformation goes to F0. F0, if you take a small deformation, remains F0, but in the large, you get F2. So this shows that Fn is only rigid. So this is the model for n equals 0, and then F0 is P1 times P1, or for F1, which is the blow up of P2 in one point, and no Fn is globally rigid. Okay, so this was now for curves. So n, so dimension of x equal 1, we get that h2 is 0, and so the deformation of a curve is smooth of dimension equal to h1 of theta, but we are on a curve. This is h0 of 2kx, and so this dimension is 0 for g equals 0, 1 for g equal 1, and 3g minus 3 if g is at least 2. So in dimension 1, it's well known that the only rigid curve is P1. So let's go to dimension 2, and I should say that I will mainly focus on this case. And when I mean dimension of x equal 2, sometimes I will say that I will denote x by S, which means a smooth surface. Now, in this case, becomes very important the Enriquez-Kuranishi inequality, because the dimension of the formation of S is at least minus chi of theta S plus h0 of theta S, and this is just 10 chi of OS minus 2k squared S plus h0 of theta S. And this is called the Enriquez inequality. So the Enriquez inequality is that the dimension is at least 10 chi minus 2k squared. This was the inequality. Since here you have the dimension, h0 is positive, of course, this dimension is greater than 10 chi minus 2 squared. So this is already, this is what some people call the expected dimension. Okay, so let me proceed with dimension 2, and you might think that what happens in dimension 2 should be known, but this is not true. So the first theorem which I want to explain, it's not so difficult once you know the classification of surfaces, but apparently I've never seen it anywhere. And this is joint work with Ingrid Bauer. And it says the following: assume that S be a rigid, smooth projective surface. I think one can extend also to non-projective, but we have not yet done this. Then, okay, we assume that it's rigid. Then there are two cases. The first alternative is like, well, most of the case, either S is of general type, and this implies that it is globally rigid. So I will not, let me comment on this fact. Globally rigid follows from the fact that there exists a moduli space. And otherwise, S is a del Pezzo surface of degree the degree is k squared of S, at least 5, which means either P2, P1 times P1, and more generally the blow up of P2 in k points, where since k squared is at least 5, k is at most 4, and the points are not infinitely near and in linear general position. So we have already seen, if you blow up a point, you get F1, and either you blow up 2 points or 3 points which are not collinear, or 4 which are in the. And in particular, in case 2, the only globally rigid surface is P2. So you see, the reason why I also speak about dimension 2 is that in higher dimension there's been a lot of work, especially Mock and Siu and others and Huang, concerning the question of global rigidity of locally rigid manifolds. So let me explain. In the case of surfaces, it just follows for the following reason, that for F1, I've already showed that it deforms, and in these other cases, if you blow up 3 points which are non-collinear, then you can deform these 3 points so that they become collinear. And then you get a so-called weak del Pezzo surface. It contains a -2 curve and is not isomorphic. And so in this case, it's not so difficult to see. Okay, so I think I would like, before I go to the proof, let me make some easy remarks, is that given this example, then you can construct more in higher dimension, and so and the first thing is that if x, you have this proposition, if x and y are infinitesimally rigid, then also the product is provided that h naught of theta x equal times h1 of oy is 0 and h naught of theta y times h1 of ox is 0. So infinitesimally rigid means that h1 of theta x is 0 and h1 of theta y is rigid, and then either these two vanishes, no vector fields, or they're both regular, and it just, the proof is the Q-net formula. That theta x times y is the direct sum of the exterior tensor product theta x, exterior tensor product of y, direct sum with ox, exterior tensor product theta y. And so that's how you get this easily, and so you get more example. And another useful proposition is that if x prime over x is étal, and x prime is rigid, implies that x is rigid. And the proof is also quite easy, because shrinking, I claim that the deformation of x embed in the deformation of x prime, since étal coverings, they correspond to the fundamental group, and the fundamental group of x is equal to the fundamental group of the whole family for b small. And so this fundamental group remains the same, and you can take this covering. Now the converse is false. And the easiest example are the so-called Beauville surfaces. So Beauville surfaces are among the easiest example of rigid surfaces. So you have C1 times C2 divided by G, and you assume that the action is diagonal, and the genus of C1 is at least, well, it doesn't matter. Of Ci is at least 2, and we want that Cj over G, we want that Cj, this action makes Cj a triangle curve, so this is P1, and the branch, the covering is branched in 3 points. And the Bouville surfaces are the easiest example of strongly rigid surfaces. And the moral of this example is that, of course, the Bouville is rigid, but C1 times C2 is not. Because to deform S, you must preserve the curves and the action. And in fact, what is rigid is this action, because essentially it comes out to H1 of vector fields with zeros in these 3 points. Okay, so this is this proposition 2 will become useful later on. Now, I would like to give you the idea of the proof. Okay, I want to avoid the shade. So idea for theorem A. The first basic tool is a theorem of Kodaira, proved in the 60s, and is the stability of exceptional curves of the first kind. So by Kodaira, so assume that S is the blow-up in one point of S prime. And then the theorem of Kodaira says that all deformations of S make this -1 curve survive, and by Castelnuovo-Enriquez contraction theorem, you have a deformation of S prime. So these are deformations of the pair of S prime and P. So the first thing which I want to explain is that how can we have a non-minimal example? So assume S is not minimal. Then there is a chain of contractions of blow-ups. S is S0 and S1, Sk is S prime, where this is minimal. And Si is the blow-up of Si plus 1 in some point Pi. Now, the elementary idea is simply that you can, if S is rigid, each time, if this is rigid, this means that whenever you move the point, they remain isomorphic. So this means that the automorphism group of S prime is transitive. So S rigid implies S prime is rigid, and the automorphism group of S prime has dimension at least 2k. In particular, it is transitive. So now let me explain something which is known to experts, but essentially now, since the automorphism group is as positive dimension, there are two linearly independent vector fields. So I'm assuming it's not minimal, so there exist two independent vector fields. And removing this 0, we get an exact sequence 0 OS prime D1 plus OS prime D2. This goes to theta S prime. And then these generate everything. I've taken away and these generically generate, and so this has support of dimension 1. Now from this exact sequence, you just take the determinant. Now the determinant of the dual of omega 1 is minus ks. So it follows that minus ks prime is at least d1 plus d2. And I've been forgotten these curves here. Now, if the minus k is effective, so either, there are two options, either S prime is not Neff, but if a surface is not Neff but is minimal, this implies that S prime is ruled. And the ruled, so here I use a little bit of classification theory, the ruled minimal surfaces are just P2.
So the canonical class is not there.
Yes, thank you. Yeah. So if minus k is effective, ks prime is not Neff, and either we have P2 or we get a P1 bundle over a curve. I don't know why it follows all the time. Okay. Or the alternative, you see, minus k is is effective. So either is a curve and is not Neff, or is trivial. Well, minus k prime is trivial, and d1 and d2 are 0, and it follows, and theta S prime is O plus O. And this implies that S prime is a complex torus. Well, since it's projective, it is an abelian surface. Which is not rigid. Now, P2, we know is rigid. Now, the P1 bundles over, now, if the genus of C is 0, so if S prime is ruled, and the genus of C is 0, then we know that is F0 or F1. Now, if the genus of C is at least 1, then I claim that S prime is not rigid. Because S prime is obtained, is birational to C times P1, and I can deform C. So this is a part, I said, idea. What you do is that you start with the product, and then you perform so-called elementary transformations. And this you can do by moving C, okay? So this is, you must know what is an elementary transformation, which you blow up a point in the fiber and contract the street transform, and so this shows immediately that the root case. And Okay, so maybe I don't want only to explain this theorem, but maybe this is technically simple to explain. Now, okay, if it's of general type, well, there's nothing to prove. And then, for instance, Kodaira dimension S is 0, then we use the, so if S is minimal, and Kodaira dimension is 0 or 1, then it follows that k squared is 0. Now I use this inequality of Enriquez. 10, the deformation space has dimension at least 10 chi minus 2k squared, but k squared, which could have given trouble, is equal to 0. So the conclusion by the Enriquez inequality implies that chi is 0, and this excludes Enriquez and K3s. And then we know that the rest, it's abelian surfaces are not rigid, and hyperelliptic or bielliptic surfaces are not rigid. And also abelian surfaces. And maybe in the case of Kodaira dimension 1, it's more subtle, but it's similar to this Beauville construction, and you get an elliptic curve. But the group acts on the elliptic curve by translation, and so you can deform the elliptic curve. Okay? So it just goes by Chirac. But so let me finish here, because I would like to. Now, okay. What are the known examples? Of rigid surfaces of general type. So the first are the ball quotients. Which are strongly rigid. Ball quotients. The second example are polydisk quotients. So somehow are the non-compact duals of this. So we have so irreducible by these quotients. S is B1 times B1 over gamma. And gamma, the projection of gamma in both factors, or at least the subgroup of gamma, which doesn't exchange the factor, where gamma is irreducible. And these are also strongly rigid. By essentially Yost and Yau, and Mock, and so on. And then there are, again, by these quotients, we have the Beauville surfaces. Then we have, yeah, maybe I should call it 2b. 2a and 2b, because they are just by these quotients. And then 3, these are the most ONCU examples. They are branch covers of ball quotients, and they have C1 squared divided by C2 is very close to 3, so they're not ball quotients. And the amazing fact is that they have a metric of negative curvature. And this implies, since they're compact, by the theorem of Cartan-Hadamard, that the universal covering is just diffeomorphic to R4. Then there are some rigid Kodaira fibrations. So what is a Kodaira fibrations? This means F, a mapping from S to a curve, such that it is differentiable bundle. But not holomorphic bundle. And these were constructed together with Rolensky when we were trying to maximize the slope of this, but we could only reach 2.66, which, and if you look now, in this case, again, the universal cover is a B2 bundle over B2 differentiably, because you see, you can take, in this case, here, the genus of B is at least 2, and the genus of the fiber is at least 3, and this implies that, again, the universal covering is diffeomorphic to R4. So here comes the connection with the topology, except in the ruled case, whenever we take the known rigid surfaces, we always have that a k pi 1. Remember that X is a k pi 1, means that the universal covering is contractible. So now what are the new examples? This page disappeared. Let's see. Okay, so let me describe the BCD surfaces. So these are surfaces. You take P1 times P1, and then you take the horizontal and vertical line corresponding to 0, 1, infinity, and the diagonal. This has a projection to P1. And then I take S is the minimal resolution of Y So here I take coordinate xy, here I take coordinate x. And now I take a Galois cover. So instead of cyclic as Xavier, we take z mod n squared. And I take Wn is x0, x1, x1 minus x0 to the n minus 2. You see that this is divisible by n. And I take the nth root of y0, y1, y1 minus y0. And then these are the three horizontal lines, but there is the diagonal, and so I take y1 x0 minus x1 y0 to the n minus 3. Now I want to make everything divisible by n, and so I add x0 cubed. Now, so I get a mapping here. I get y, the desingularization is S, and then this gives me a map to a curve B, and B is the Z mod n cover of P1 given just by the first nth root. Okay. So in order to make the desingularization, you have to blow up these 3 points, and so you get Z del Pezzo of degree 5. This is a beautiful surface which admits the symmetry of the symmetric group as 5, and this will be quite useful in the sequel. Now, why were we interested? So this is Ingrid Bauer and this is Detweiler. So with Detweiler, we were interested about this because these surfaces have some remarkable feature. F from S to B is the Albanese map. So these are not Kodaira fibrations, but they are close in some spirit, which I will explain. The genus of B, I have to take n not divisible by 2 or 3 in order to get the smoothness of the surface. The genus of B is n minus 1 over 2. The genus of the fiber is equal to n minus 1, and there are only 3 singular fibers, which are two smooth curves of genus n minus 1 over 2, meeting in one point transversally. And the slope is bigger than 2.5 and small or equal to 3, equality equal 3, if and only if n is 5. And the reason why we were interested is that there was a long-standing question by Fujita, which he posed in '82, and in this case we have that F lower star of the relative dualizing sheaf is not semi-ample. Which, against a question by Fujita. Now, how do you prove that this bundle is not semi-ample? If I call this bundle V, in fact, V is an ample bundle plus a unitary flat of infinite order. So unitary flat comes from a representation of the fundamental group, and this, the image of this representation is infinite. And in fact, one can prove that a unitary flat bundle is semi-ample if and only if the representation is finite.
So by semi-ample, you mean you go to the projectivization?
Excuse me?
What does it mean, semi-ample?
Semi-ample, everything on a vector bundle, it means you take the projective bundle and you take the O1, which is defined by V, and then if O1 is ample, so semi-ample means that the multiple is globally generated. And I think it was believed for a long time, also Collard admitted that he believed that the question would have a positive answer. Now,
The determinant is ample.
the determinant is ample. Yeah. I mean, here is trivial, and this is... so it's really, essentially, the idea, I mean, in fact, I guessed this fact that it was sufficient to have infinite order. So you see, this is a family of cyclic coverings of P1 branched in 4 points. Okay? So now the Hodge structure decomposes into characters. And it has the special feature that if you take a character and the opposite character, like in the lecture of Alexander, the sum of the dimension is 2. But if it's 1, 1, then it's ample. You put them together. But if one of the two is 0, which happens simply because 1 plus 1 plus 1 plus n minus 3 is n, there is a very simple formula by the linear Mosto, and you prove that V1 is 0, and so V minus 1 is flat. And anyhow, I don't explain. So now what is, after we discovered these surfaces, I realized that actually with Ingrid we had already constructed these surfaces for n equals 5. And in fact, these surfaces are related. They have an unramified covering, which is and is a Hirzebruch Kummer covering. Over a complete triangle, quadrangle. So you take 4 points in P2. There's another way to see the del Pezzo surface, and then you take the nth root of all these quotients of linear forms. Now, it's still there the criterion that to prove that something is rigid, it's sufficient to prove that there are quotients. So now the second theorem is that this example and the Hirzebruch Kummer coverings, these new examples, these are new examples of rigid surfaces. So I have minus 1 minute, or can I just put 2 questions? Okay, so at any rate, I was hoping that for this conference I would have time to do some calculations. So let me put question 1. So now these are rigid, so it's a general question, is that all the examples of general type, they're kappa 1s. So they will be, in any case, interesting. It's either rigid k-pi 1s or rigid non. So for n equal 5, there are Born quotients. And so many properties hold for n equal 5. And so question 1, are they k pi 1? And the question 2 is whether, do they admit, so what would be nice is to show that they have a metric of negative curvature. And the third question is, are the other example by Hirzebruch rigid? So the other examples are just the configuration of lines is the flex configurations of a cubic or the dual configuration. And let me stop here.
Are there any quick questions? What did you know about question?
What do you exactly know about question 1?
Okay, so about question 1, there is, I know that the universal covering is a CW complex of dimension 2. It's times like, okay? So now, since what is important is that this fibration is homologically trivial, locally trivial, okay? So there is a way, so you know that since it has dimension 2, you only have to calculate the second homology. And so, and then I have a way to phrase the condition in terms of independence of vanishing cycles, and this I didn't finish. I mean, this I should maybe need the summer to finish that. But of course, another hint for the negative curvature is that if you take n divisible by 5, then you get branch covers of these Born quotients. Now, if you use the technique of CO, except that here is more difficult because you get non-smooth but normal crossing, it seems possible to be able to patch some negative curvature, some metric of negative curvature, at least when n is divisible by 5.
Okay, so if there are no more questions, let's thank the speaker again.